Alright, another graph physics presentation. This one on the Doppler effect again, and Professor Lewin's argument that somehow it matters whether the transmitter or the receiver is moving. And totally unresponsive comments, in my opinion. So let's do, I guess, the jerk first. Lights out in random, whatever this means. So we will have loaded the drawing, of course. So let's do the comment, and then we'll go to the drawing. I could make that bigger, probably. I'm going to keep changing things. This is sort of annoying. Alright, anyway. I think Lewin misspoke when he answered your post because he was getting flustered. Okay, yes, he's a professional physicist. Long career as a teacher, and he's flustered by a question. Since he's not used to rude asshole. Okay, so I was rude somehow by merely stating, well, what about the scenario where two people are talking across from each other? How would it matter? How does one person's conversation not, because they're exact opposites. Where's the lack of symmetry? Show me the lack of symmetry. That's being rude. So again, you can't even ask a question without being considered rude, because you're not paying homage to God. I have to actually call the Dalai Lama your eminence, or whatever he likes, the Holy One. You know, I have to call him some kind of crap, or I'm automatically rude. I have to acknowledge that he's a gift from God, or I have been rude. Alright, coming onto his channel. So first off, I think it's just completely idiotic to say I was rude in any way. I made a deliberate effort to indicate I am not attempting to be argumentative for the sake of argument. I'm asking for clarity. Anyway, the unintuitive effect of which he spoke applies whenever there are waves. So again, he made it very specific. He said it twice in the video. This only has to do with sound, and it doesn't affect electromagnetic waves or GR effects. He said that specifically. They just keep. I mean, this is just how these people are just so full of shit. Anyway, the unintuitive effect of which he spoke applies whenever there are waves traveling at a constant speed with respect to a fixed reference frame. So, more crap. This has to do with sound. He was very specific. It only affects sound. Sound is the thing that does the breaking of the sound barrier. It does have some unique features. Anyway. And since sound travels through a medium of air, it ipso facto travels with respect to a fixed reference frame. Completely irrelevant, in my opinion. Point out how it's an asymmetrical frame. And again, I specifically asked in the video for, just show me a sound experiment where moving the transmitter was different than moving the receiver the exact same amount or speed. If I just reverse the roles of the transmitter and the receiver, that somehow I get a different effect. Show me the experiment. Also, you don't have to do an experiment. Well, I think, okay, if you want to say you've proven something, you sort of need experimental evidence, or else it's pretty much just the rest of physics, just made up crap. You don't have to do an experiment to find black or dark matter. Just make it up as a theoretical mathematical possibility and then believe in it. That's how you do religion. You don't need evidence that God exists. If you can imagine he exists, that's all you need. You need an imagination. I can imagine it. I can break lots of physical rules and imagine him existing. And so there, I'm done. I don't have to have anything called evidence. Alright. To understand the principle. I don't think there's a principle involved. That's my whole point. You're saying it's a principle that the sound is asymmetrical. That moving transmitters creates more or less Doppler effect than moving the receiver. I'm saying I don't see any theoretical reason for that asymmetry. I see no mechanical reason for the asymmetry, so I want evidence of the asymmetry. You're not providing that. Alright, So now, oh, just think, okay, I can do that part, of a wave source, like a duck swimming. Well, that's, we don't have to go that slow. In a body of water. If the source moves, so now we're in water waves. If the source moves away from the duck, then you can count how many waves per second there are. The source moves away from the duck. Then the waves get longer because it's moving. See, which way is the duck moving? So you have the source moving and the duck moving. But you haven't even told me what directions they're moving in. And if the exact same wave source is stationary, you can calculate the waves per second relative to the duck in that case. I'm not arguing you can't understand. I'm saying go ahead and show me the evidence. Show me the evidence that moving the duck stretches the waves less than moving the source of waves. And if you were moving away from the source, the sound source, then the basic algebra, so here we go again, this idea that somehow basic algebra demonstrates this asymmetry, when I'm saying, how does it? How does moving transmitter do something different than moving receiver? Doppler effect is something produced by emitters and produced by receivers. They produce it, and they produce it proportionally. Just multiply the interval by the ratio of your fucking speed derived by the speed of the wave. Why should I do any of that? Again, I'm asking for a simple thing, a sound experiment, where you demonstrated that if I move the speaker towards me, I'll get a different Doppler effect than if I move my head towards the speaker. Well, show me where moving the speaker creates more Doppler effect than moving my ear towards the speaker. Show me that experiment. Fuck. Alright, think of it as a panning shot through a camera lens at a fixed rate. So now he's using light waves. So now the very thing they said it doesn't apply to, the electromagnetic spectrum, the very thing he explicitly said this doesn't apply to, and he's giving me an example of it. Just as he did in his own video comments where he started bringing up Sputnik, when he said this doesn't have anything to do with the electromagnetic radiation spectrum. It only has to do with sound. I mean, you can't see how insane your arguments are here. Alright, anyway. A camera lens at a fixed rate over the surface of the water and making a video recording. The wave interval would be calculated this way. Well, you say it would be. I think it's quite obvious. The waves travel through a point in space. And all you're doing is saying, if I'm moving the point of space exactly the same speed that the emitter is moving, well, then the frequency is going to be exactly the same. And if I reverse the scenario and I'm moving the emitter away and I'm moving the receiver towards, I'm going to get exactly the same effect. It's like basic algebra. So you keep saying it. Where does the algebra create an asymmetry? Where is the physics for the asymmetry? You are an unmitigated ignoramus. Okay, so, alright, I'll draw some of this, I suppose. But I don't know what, what the argument is. Alright, we haven't gotten to the sound barrier part, so I don't know if this is a point in illustrating this part, because they don't really understand what a sonic boom is. I mean, Professor Lewin described it. I could argue his description of a sonic boom and say, that's not correct. Alright, so let's read the other comment first. Alright. So, Delta Nor says, Scenario 1, transmitter is stationary, receiver is moving to the left at the speed of sound. So I already pointed out how, yes, at the speed of sound, or anything that adds up to the speed of sound, okay, in the sense of the waves, if you move two things away from each other at 400 miles an hour, they won't hear each other. Okay, they can't communicate. It's not possible. So as soon as the combined distance, speed, the rate at which the two are moving away from each other exceeds the speed of sound, the two objects will no longer be able to hear each other. Zero sound is transmitted. Not that it's a zero frequency. There's no sound. There's zero sound, not zero frequency. Anyway, the sound waves move at the speed of sound, so they don't even catch up to the receiver, and so the resulting frequency is zero. Well, obviously the frequency isn't zero. There's no sound. The sound is zero. There's no potential for frequency. You can't have a frequency if you didn't receive the sound. So it's not even a correct thing to say. Scenario 2. Transmitter is moving to the right at the speed of sound. Receiver is stationary. So now, I don't know what to the right means. So that's towards or away. I mean, you could have made that clearer. Look, if the transmitter is moving away from me at the speed of sound, I hear nothing. If it's moving towards me at the speed of sound, I hear a sonic boom. But I don't hear it the way Lewin described it. Okay, so he says the transmitter, so in this scenario I imagine he's saying that the transmitter is moving towards you at the speed of sound. So it's essentially an object moving towards you at the speed of sound, which is a sonic boom producer. The transmitter emits a wave peak at point 0, whatever that is, whatever point 0 is. And then the wave moves to the left at the speed of sound while the transmitter moves to the right at the speed of sound. Well, now you have the two things moving into each other. I don't know, both of them moving the speed of sound towards each other? You can't do that. Well, I mean, you can do that, but all you're doing is sonic booming each other. You won't have a conversation that way. When it emits the next wave peak, the first peak, theta, no, that's lambda or whatever, well, wavelength, to the left of its origin, 0, and the emitter, lambda, to the right of that origin, 0. Hence, the total wavelength is 2 lambda. So you're jumping between frequency and wavelength now. And they're not exactly the same thing. So he says the resulting frequency is F equals frequency divided by 2. So again, how does this show asymmetry? Alright, so in Professor Lewin's video, he talks about how a sonic boom is created. And he uses an airplane as an example. And he says something like, the noise that the airplane is making, all the sound waves pile up at 0 frequency, okay, and that creates a sonic boom. So he implies that the sonic boom is somehow made of this frequency constipation, and that there's somehow an explosion of the constipated frequency. When I would argue that I could make a very stealthy flying machine that created no real noise, vibrations as it moved very fast, and it'll still make a huge sonic boom. The sonic boom is a byproduct of how much air you're moving. So it has to do with, obviously, you have to have a mass. It'll be a mass equation in the sense you can't give something with no mass enough velocity in a thick medium like atmosphere. But regardless, it'll have to do with displacement of air. So how if the thing's flying this way, it moves more air than if it flies this way. But it's still a massive object, even if it has a really aerodynamic profile. It's still a massive object moving a massive amount of air, and so the sonic boom will reflect its size. So the bigger the thing is, the bigger the sonic boom in terms of its amplitude. But it's not made of the noise the object was making. It's made of the fact that you just broke the tension between all of the atmospheric molecules, and it's that broken tension, so a bunch of different frequencies that you're creating because you just broke the tension between all of the molecules. So they're jiggling in like a heat effect, noise effect, and that's why the sonic boom has lots of frequencies in it. And it just sounds like boom, is because it's a bunch of jiggling. And it has nothing to do with how much noise it was making previous to sonic boom. It has nothing to do with the compression of some kind of waves. It just has to do with the fact that once you go faster than the speed of the medium, the tension speed, you smash the little elements into each other too fast for the tension to take care of it, and the actual atoms are now crashing into each other. So theoretically, the way sound works is there's tension between the atoms that is magnetic, and when you push them, they push away from each other without actually hitting each other. The atoms never hit. They just bounce off of each other's force. So the idea is you're throwing the magnet so fast, so let's say there are two magnets, you push one magnet so fast that the force effect can't move it quickly enough, and the thing hits, the magnet actually hits the other magnet. So there's a speed that you could throw a magnet at another magnet. You could throw it at one speed and it'll bounce off. But there is a speed where you can go fast enough where you actually hit the magnet and you don't hit the force. The force isn't strong enough, and the speed goes right through and hits the magnet. So a sonic boom is basically caused by the atoms actually colliding with each other. That is, the electrons are now engaged with each other. You've broken the membrane, so to speak, the force membrane of the atoms, and that's creating the sonic boom. Alright, so now let's go to the drawing, and I'll just make the simple illustration. So again, I requested evidence. I was given nothing again, but more just do the math. No, I want to see it. I want to see it happen. I want you to show me the asymmetry in some other form than going faster than the speed of light or slower, and then going where you can't even receive the sound. Those two scenarios don't prove anything. So let's do this. Video up. Alright, so what do I want to draw exactly? Alright, so let's take two objects moving towards each other. And let's make this one go, just to exaggerate things, so we'll make this one 300 miles an hour and this one's going 400. And let's say the speed of sound is 699, just for, just make it arbitrary, just make it simple. So we're 1 mile an hour over the speed of sound when you combine these two. Well, that doesn't mean you'll hear a sonic boom. So even though their combined speed is 700, there's no sonic boom, because no individual object is breaking the sound barrier. No individual object is forcing atoms into each other. They're still just creating sound. And so this thing's sound is going to be, the frequency is going to be compressed, and so these two will both hear the same compressed sound if they're transmitting to each other. Now if we make this one of them exclusively a receiver, and so for this example we'll say this is the receiver and this is the transmitter. Now we can see that the combined frequency is going to be the compression created by 300, okay, and the receiver is going to add 400 compression to the frequency, and so the frequency will be, essentially it's going to be twice the speed of sound as the effect, and so there'll be twice the frequency. Yeah, it should be. I mean, if you're going this, if your total speed is the speed of sound, that should take a frequency that's this big, and it would cut it to this big. So the pitch would go up by 2. Now if I reverse this, make this the transmitter, and I make this the receiver, I changed absolutely nothing. It's exactly the same amount of total compression of the sound. So the total compression is exactly the same, either way. Now if I make them going away from each other, or one going away and one going away and one going towards, well then we're back to the same scenario again, where if I use the same numbers, you could see if they're both going 300 miles an hour, you could see, well, that ain't going to make any difference. One's going to undo exactly what the other one causes. So the stretch in the signal created by this one, it's getting wider, the compression here will be exactly the opposite. So the net effect is they'll hear the same thing. Now if I make this 400 and this is 300, all right, this one's going to create a bigger stretch, and this one's not going to undo entirely the stretch, so you'll have a 100 left over, so you'll have a 15% increase in the pitch. But it doesn't matter whether I make this the receiver or this the emitter. You'll get exactly the same effect. So show me the asymmetry in any circumstance where you keep the speeds reasonable. Like I said, if they go in the same direction, you can go all the way up to the speed of sound and you're still safe for one of them. You could make both of these go 600 miles an hour and you're still okay. But as soon as you go over the speed of sound, then you're done having a conversation. So I don't know, it doesn't seem like there's anything else to illustrate here. I can find I can't come up with a scenario that creates a problem. Like I say, even when they're moving towards each other, I can't create a synthetic sonic boom unless one of them is actually going faster than the speed of sound. There's no sonic booms until one object moves faster than the speed of sound. You can't combine two speeds to create a sonic boom. And likewise, subtracting speeds, you have to have one of the objects go actually the speed of sound before, well, obviously, like I said, like I pointed out, if the two objects are moving away from each other, the emitter is moving this way and the transmitter is moving this way. So transmitter, receiver, they're both going 500 miles an hour. Okay, yes, then the total is well over the speed of sound, so there'll be no sound transmission from the transmitter to the receiver. But if I make it 200, okay, then it's a total of just 400, so I'm well under the speed of sound. So all I'll do is stretch the frequency. Both of them are causing stretch, and so it'll be 50% lower tone. The frequency will be stretched. It'll be redshifted. But it doesn't matter if I make this the receiver or this the transmitter. How can it possibly make a difference? Can't make a difference if I make one of them going 300 and one of them going 200. How does it make a difference whether this is the transmitter and this is the receiver? How is the byproduct heard sound any different? Other than the fact that obviously if you change the receiver speed, you're going to hear, because the 100 extra is coming from the receiver. So obviously the pitch is either higher or lower depending on which one you make 300. But there's no asymmetry in the fact that you're creating more shift. And certainly there's nothing that would apply just to sound. This rule, the 200-300 rule, would also affect EMF or any other kind of moving radiation. Anything else moving at a frequency would be affected by that rule the same. It wouldn't be exclusive to sound. Again, he said this effect is exclusive to sound. He said it twice in the video. Again, where's the experimental evidence demonstrating any such effect? That's all I can do.